Okay, so let's do another example with logistic regression. So I'm now, FYI, calling these instead of day 2 and day 3 since we don't really have that anymore. Our first file was day 1, and now I'm just going to start calling them part 2, part 3, etc. Okay, so we have this data set called losing, which you can bring up from Moodle and read it into R. But basically there was a random sample of 446 teenagers from 14 to 18, and they answered the question, on an average school night, how many hours of sleep do you get? And they gave a number of hours, but then the results were coded so that yes meant they got 7 or more hours of sleep on average, and no meant that they got less than 7 hours of sleep on average. Alright, so the first thing I did, and again you can pause this video and run this code, or maybe you started by running all the code yourself and now are going through the video. Whatever way works for you is fine. So these commands kind of summarize what was in the table. So for example, for all the 14-year-olds, 34 of them were coded as a 1, that yes, they got 7 or more hours of sleep a night, which is 0.739, or about 74% of them. Now, the commands that I have here in R, these commands don't create exactly the table that's shown here. I kind of put that together myself. I did not take the time to try to come up with code in R that would make this table come out. But if you're interested, have at it and let us know what you come up with. So then I wanted to plot the proportion of yes against age. And so I created a new data frame. So basically I made age as a variable from 14 to 18, and then I created this prop 1, which comes from this sleep proportion up here. But basically that gave the proportion of zeros at each age and also the proportion of ones at each age. So I basically asked it for the second line of that, the second row of that, so that it's giving me the proportion of yes, or 1, as it says here, prop 1. So then I made this summary data as a new data frame that had age and prop 1 only. So now I created a scatter plot of prop 1 for the vertical axis and age for the horizontal axis, and I did put some x and y limits on there, but let's see what this looks like. So the thing is that we could fit again a simple linear regression model for this, but it's not advisable. So once again you can see that if you actually put the regression line there with the data, you immediately see that you will eventually get some probabilities bigger than 1 and less than 0. So as with the previous example, the problem with trying to fit a straight line to these probabilities is that you end up with probabilities that don't make sense. So what we want to do is that same log odds transformation. So I just copied and pasted these lines from the previous. They're also in the previous file, the day 1 file, but just again it's helpful to have the definitions here. So we are starting with pi, which is the probability of success, or the probability that the response is 1. Then we have the odds, that is that success probability divided by 1 minus the success probability, and then we take the natural log of that and we have the log odds. So we make this transformation from pi to the log odds. That's called the logit, or the logistic transformation. Now in this case we didn't have only zeros and ones. Well, we originally did, but then we grouped them by age, right? So I added now these two variables to my summary data set. So this one is finding the odds of a yes response. So you can see that it's taking prop 1 over 1 minus prop 1, that is pi over 1 minus pi, and calculating odds of 7 or more hours of sleep on average. And then I added the log odds Now this is based on our data set, right? It's based on a sample of data. So now we have the log odds as well. So now I created a linear model that is predicting the log odds of yes against age. So now you can see the scatter plot with the regression line, and again, it doesn't look really that different, except what we have on the vertical axis is not the probability of yes anymore, but it's the log odds of yes. So that's something different. Okay, so we've transformed the probabilities into log odds, and then we're fitting a linear equation to those log odds. Okay, so let's look at log odds again, just to try to keep making you more and more familiar with this. So we have the value of pi in the top row, which again we can think of as A over B. That is the probability of success. And then I mentioned in the previous video that one of the ways you can get to odds from that is to take A over B minus A. So for this first column here, the probability of success is 1 out of 20. That means out of those 20 possibilities, one of them is success. That means the other 19 must not be success. So the odds of success are 1 to 19, right? So the denominator here of 19 comes from doing 20 minus 1. And so on down the columns, right? Let's look at the one for 4/5 just as an example. So the probability of success is 4 out of 5. That means of the 5 possibilities, 4 of them are success. 1 of them must not be success. So the odds are 4 to 1, or 4 over 5 minus 4. Now the bottom row is just as it says, the log odds. So you're taking the natural log of each of those values in the odds row. And of course you remember from your previous schooling that the natural log of a value between 0 and 1 is negative, right? The natural log of 1 is 0, right? So the natural log of a value between 0 and 1 is itself negative. The natural log of 1 is 0. And then the natural log of a value bigger than 1 is positive. All right, so there's two things about this log odds transformation that are important for the work that we're going to do. One is that we have a one-to-one relationship here. So other than the values of 0 and 1, there's only one value of the log odds, right, for any value of pi. So that means that we can reverse the transformation, which is important because we might, generally we're interested in understanding the probability, but the linear model that we're creating doesn't speak directly to the probability, it speaks to the log odds, right? Now the log odds can be anything between negative infinity to infinity, which means it's appropriate then to make this linear predictor for that. Okay, so we basically have 4 probabilities that we're working with, and we have these true values. So for a particular value of x, little p is the true probability of success for that value of x, like for a particular age, whereas p hat is based on the age for example, in our data set, the age 14, just in the collected data, right? So that's the probability of success based on the sample cases, as it says underneath here. And then there's a true value of pi based on the model, and then there's a pi hat, which is the probability of yes based on the model. It's a fitted value. So we have the true value versus the fitted value. We have what's actually true and what's based on the model, right? So if the model were exactly correct, then the little p and the pi would be exactly the same thing, and they would be estimating the exact same number in the pi hat and the pi. Okay, so basically for the fitted values in the right-hand column, we can use our model to come up with those. So first of all, this first row here, these are the prop 1 values, right? So when we ran the code, the previous code in R, if you were to just look at this, if you run this summary data to 3 decimal places with the new things that we've fit into it. So we have the prop 1, that's the probability of success at each age based on the cases that were in the sample. And then we did the log odds 1 that we created. I think this is a capital O actually in R. And so those again are the natural log of the p hat over 1 minus p hat. So we added that to our data set as well. Okay, and then the fitted values, so let me use a different color here. These LM2, the fitted values from the model are log odds, fitted log odds, and that's what these are. Okay, so the model basically said, okay, based on those ages and according to what the model says, I'm going to fit those log odds values. And then we're working backwards and exponentiating, and I'll go through that again in a minute. And that's how we're coming up with these bottom row values, just for the ages that were in the data set, right? So we're working backwards, we're exponentiating to get the estimated pi hat, the fitted pi hat from the model. And then I picked these other ages. Let me see if I can get another color here. How about green? And the predicted log odds, this part right here, are for ages 2, 12, 20, and 30. And then the predicted pi hat, let me pick yet another color. Is that too similar to something I already have? How about orange? Exponentiating, but based on these new ages of 2, 12, 20, and 30. Those are here. Okay, so just by way of reminder, we can go back and forth, right? So we know that the odds we can get by taking e to the log odds. So we're exponentiating those log odds. And then based on our work earlier, when we want to go from odds to probability, we know that probability is odds over 1 plus odds. And again, that we went over that in the previous video. And so that means that pi is e to the log odds over 1 plus e to the log odds, which, since we have fit log odds to this linear model, then that means that pi is e to the beta 0 plus beta 1x. Sorry, that doesn't look very good. Over 1 plus e to the beta 0 plus beta 1x. So again, the log odds is what we fit the linear model to. Okay, so if we raise e to the log odds, then we're raising e to this beta naught plus beta 1 times x.